Greeting Earthlings! If you follow the channel, you know that we are hard at work restoring the Apollo communication hardware. It all started simply enough with just the spacecraft S-band transponder and the traveling wave amplifier that we picked up from collector Steve Jurvetson. But it got progressively more complete as we found and added more pieces to this complex system, both on the spacecraft side and on the ground side, thanks to more pieces from Steve, Marcel, and other generous collectors. It's getting so involved that we had to add a replica of the control panel to manage it all. But we are far from done. The system is so complex that we still have quite a few more boxes to restore and add. For one, we have been powering it up with a modern 400 Hz 3-phase AC power supply. Now, wouldn't it be nice if we used the real spacecraft power supply inverter instead? Mike and Eric.
Hello.
What is this big chunk of metal you're working on?
It's very heavy. This is a Block 1 inverter. So one of 3 of these that were installed in the command module that took in 28 volts DC and put out 115 volt RMS 3-phase 400 Hertz AC power.
The good avionics AC.
Mm-hmm.
So 1 kilowatt, 1.5 kilowatt-ish each, right? One for each fuel cell, which was 1.3 kilowatt, something like that. To better understand the role of the inverters, we need to look at the Apollo Command and Service Module power system for a moment. The heart of it consists of 3 fuel cells, which make electricity by reacting oxygen and hydrogen stored in liquid cryogenic form. This produces both electricity and drinkable water. We explained the fuel cells and their failure on Apollo 13 in a previous episode, which I'll link in the doodly-doo. But I'll recap quickly here. The fuel cells were quite powerful at a max rating of 1.42 kilowatts each. They produced the power for the whole spacecraft in the form of DC voltage, varying from 27 volts to 31 volts, depending on how hard you ran them. They had 3 fuel cells, but the whole mission could run on only 2, and as NASA diminutively puts it in their operations handbook, you could successfully terminate a mission on just 1. Of course, on Apollo 13 they lost all 3, and they were lucky to have the LEM attached, or the situation would not have been recoverable. The fuel cell power was distributed over thick conductors called buses, main DC bus A and main DC bus B. Normally, fuel cell 1 powers main bus A, fuel cell 3 powers main bus B, and fuel cell 2 is connected to either A, B, or both as a backup. And that's why you hear the famous main B bus undervolt call on Apollo 13.
Okay. Stand by, I got a problem. You see a hardware
They had just lost fuel cell 1 and 3. At the Apollo 13 accident time, the backup fuel cell 2 was connected to bus A, so only the bus B voltage went to 0, hence the main bus B undervolt caution light. However, you can manually switch any fuel cell to any bus, and you hear them at first try to reconnect fuel cells to the default configuration, cell 1 on bus A and cell 3 on bus B.
Lady time? Go ahead. He's got fuel cells 1 and 3 are offline. We've got main A volts, we have no main B volts. Have them attempt to reconnect the fuel cells. Fuel cell 1 to main A, fuel cell 3 to main B.
3 to B. Okay.
Let's just try that.
13 Houston, we'd like you to attempt to reconnect fuel cell 1 to main A and fuel cell 3 to main B.
This will of course fail as both fuel cells are already gone, and the remaining fuel cell 2 will be nursed to last an agonizing 90 more minutes before being shut down.
Okay, Houston, I'm showing, I tried to reset, and fuel cell 1 and 3 are both showing gray flags, but they're both showing zip on the flows.
I copy, flight.
We copy.
Let me commiserate on that.
Note that on this drawing from Apollo 17, fuel cell 2 has a big 400 amp hour battery backup. Couldn't they just switch that on? Well, you bet they did not have that one on Apollo 13. It was added on 14 after the accident. Hindsight is always 20/20, as they say. But enough for the DC power. We want to discuss AC power. The spacecraft had 2 AC buses powered by 3 inverters, one of which we are about to open. The inverters converted the DC power from the fuel cells to AC power, namely 115 volts, 400 Hz, 3-phase AC, which had been the standard for aircraft AC for over half a century. The inverters were quite beefy, rated at 1.25 kilowatts each. Since we have 3 fuel cells and 3 inverters, you'd think one inverter would be assigned to each fuel cell, but the system is more flexible than that. As you can see here, inverter 1 is powered by main bus A, inverter 2 by main bus B, and inverter 3 by either main A or main B. Each inverter AC output can be connected to 2 buses, AC1 or AC2. In the normal config, inverter 1 powers AC1, inverter 2 powers AC2, and inverter 3 is on standby, connected to nothing. Note that unlike the fuel cells, which you could pile up on the same DC bus, you cannot connect 2 inverters at the same time to the same AC bus because of phase issues. However, there was flexibility to connect any inverter to any AC bus if needed. A complicated set of motorized relays implemented automatic interlocks, preventing to connect more than one inverter at a time to the same AC bus. So you should now be able to understand why they lost AC2 on Apollo 13. Main DC bus B went down, and that's the one that powers inverter 2. So inverter 2 went down, and that took out AC bus 2, taking with it the telemetry sensors that were connected to it. Sensors that will become quite important pretty soon. You can hear them realizing that early in the debug.
It does appear we've lost AC bus 2 voltage. Main B is reading 4 volts, and that effectively takes AC2 away from us.
By the way, that was the voice of our engineering hero Cy Liebergott manning the EECOM console at the time of the accident. EECOM stands for Electrical, Environmental and Consumables. The EECOM will get quite a workout during Apollo 13 and get everything just about right in a very confusing situation. About 10 minutes after the accident, way before it will all get confirmed, EECOM reluctantly comes to the conclusion that they have lost a large amount of pressure in oxygen tank 1, lost fuel cell 1 and 3, and that they blew a sphere, which is one of their pressurized tanks.
We might have a pressure problem in the fuel cell, it looks like.
It's Charlie now.
Yeah,
Two fuel cells simultaneously.
that can't be.
Charlie?
Right. I can't believe that right off the bat, but they're not feeding current.
You got it?
Yeah, if you believe that N2 pressure, we blew a sphere.
Okay, Clyde, we got Omni Charlie and high bit rate.
Yeah, we might have lost fuel cell 1.
Okay. You
And it looks like fuel cell 3 is gone
Right.
too.
Okay.
The other voice you just heard is from our behind-the-scene hero number 2, Dick Brown, manning the EPS, the Electricity Power System Officer, in the back room. Cy will heavily rely on Dick for the whole debug. In the meantime, Cy passes on the bad news to ECS, the Environmental Control Systems Engineer.
And ECS, EECOM.
Go ahead.
Larry, I'm almost afraid to think that we lost our O2 tank 1. Or we busted the manifold or something. Why, that pressure shouldn't be down that far.
So right now the only remaining source of power is fuel cell number 2, powered by the dwindling pressure in oxygen tank 1. About 16 minutes in, EPS asks for an immediate reduction of the power consumption. Once again, the correct move.
May the main B bus
I
is
think we ought to start
offline.
powering down.
Yeah.
fuel cells 1 and 3 also off the line. Fuel cell 2 is presently on the line.
EECOM, do you want to go through that again? What do you want to power down to?
I want to power down a total of 10 amps, Flight.
A total of 10 amps.
That's firm.
Okay.
After that first emergency power down, which takes a while to figure out, we are about 25 minutes in. Cy shifts his focus to confirming the status of oxygen tank 2. O2 tank 2 would be their only hope to power fuel cell 2 if tank 1 keeps leaking out. But remember our offline inverter 3 and our dead AC bus 2? Well, Cy has not been able to read the O2 tank 2 pressure since the accident, because the pressure sensor is powered by the now dead AC bus 2. He then asks Gene Kranz to prioritize the repairing of AC bus 2 so he can check on O2 tank 2.
Hey, EPS, EECOM, go. We've got to get AC2 back temporarily so we can see what's going on with the O2 pressures. O2 tank 2 pressure. Flight EECOM?
This is a go, EECOM.
Okay, I need one thing right now. He's powering down. He's down to 41 amps total spacecraft. I'd like to get my AC2 bus back so I can look at O2 tank 2 pressure. I have no insight into that.
Okay.
Let's get, I guess we can put the inverter 3 to main A, AC2.
Inverter 3 is indeed the only inverter that can be configured to be powered by main A and can be connected to the AC2 bus. But this will not get done because Gene pushes back. He is still in power reduction mode and worried about creating additional problems.
And then
let me
we'll
ask
just
you
do
a
it
question.
temporarily.
Before you do that, would you like to make sure you got all AC loads you don't need isolated from the bus?
Nah, let's not do that right now, Flight. I think we're in good shape that way. The main A is up high enough where it can handle the inverter.
Well, the thing that concerns me is throwing equipment. We had a problem. We don't know the cause of the problem.
That's when Cy, who had suspected that fuel cell 1 and 3 were gone from the very first minutes after the accident, finally breaks the bad news to Gene Kranz for the first time. It's about 20 minutes in.
Flight, I've got a feeling we've lost 2 fuel cells. I hate to put it that way, but I don't know why we've lost them. It doesn't all tag up. And it's not an instrumentation problem, the best I can tell right now.
Okay, I'll tell you what, let's discuss this for just a little bit longer there, Cy. Capcom started moving back towards a PTC attitude.
Gene is still reluctant. You have to realize that he's on the flight loop. He has heard nothing of the backroom conversations between EECOM and EPS like we have done here, on this after-the-fact composite loop. All he's heard so far were the various recommendations by EECOM to switch things around while reducing power draw. Then Dick Brown has a brainwave. He realizes that although you cannot put 2 inverters on one AC bus, you can put one inverter on 2 AC buses. Inverter 1 is working fine right now, powered from the still good main A. That will also save the power draw from bringing up another inverter.
What's firing?
Hey, Cy. Good.
You got something
Put one inverter on both buses.
It'll
save about 4 amps. Okay, I guess this kills the PTC too.
We can try
I can get into PTC as long as I get
inverter 1 on both AC buses.
Yeah, that's the
You want
suggestion.
inverter 1 on both AC buses?
Right.
Okay.
Dodge Flight, that agrees with what
Roger.
we're saying here.
Flight EECOM.
Go, EECOM.
I got a little correction. Let's put inverter 1 on both AC buses, please.
Further 1 and both AC.
That's firm.
Gene is still nervous about the move and asks a second time.
Okay, so you want to configure inverter 1 on both AC buses.
That's firm, Flight.
You can tell he's still worried about making a blunder. He asks a third time for himself, then fully commits to it and gives the go-ahead. What they are about to discover is startling.
You want to put inverter 1 on both AC buses. EECOM and Capcom, let's do it.
Okay. 13 Houston, we need to get some more instrumentation up. We'd like you to put inverter
EECOM,
1
flight.
on both AC
Flight
buses. Over.
EECOM.
Monitor this barrel when we switch
With
it
you.
in.
Okay.
This segment is hard to hear, but behind the chatter, you can hear the answer from the pressure reading.
So that we can see if we can backtrack. to see if we can figure out what's venting.
We're cycling to 50 amps.
Okay,
In
it's
other
low.
words,
It's been low.
it would seem we
It
could
looks like
equate
the
that to
culprit is
effective
probably
thrust
venting.
and an axis,
In fact,
and then
it's
deduce
probably
what's
the one
venting.
that blew, if anything, caused the problem.
Okay, I see 19
And that might be of interest to the LEM guys.
It's 19 psi. It should be 900, not 19. The second oxygen tank that they were counting on is no more. That's the one that caused the problem in the first place. Gene is eager to find out if his caving in for the request was worth it. And Cy is so taken aback by the reading that he asks for some time to take it all in.
Okay, you got 2 good AC buses. What did all that tell you now?
It tells me that, well, just give me about 2 more minutes, Fly.
Okay, take your time.
Cy thinks the tank 2 is simply empty. One way to confirm it is by looking at the temperature.
Trying to figure out what happened to that O2 tank 2.
Right. Now our pressure still should be good. And you see we got our low point there.
Why did the temperature drop so suddenly?
Because it probably don't have anything left in it.
Yeah. Yeah, and we're losing tank 1, if we can believe it.
Losing what?
Tank 1 pressure.
Yeah.
Search
You
think
think
we
slow down?
We blew the manifold?
It looks pretty good that we blew it between the check valve and O2 tank 2.
Oh yes, they sure did blow the manifold, and then much more. They blew the whole tank. Cy will never bother to answer Gene's question. He has already moved to the next step. Tank 2 is a goner. Instead, he immediately focuses on a few more attempts to save what's left on Tank 1. EPS asks that they try to turn on the heater in Tank 1 to see if the pressure will come back up. Tank 1 is now around 320 psi and dropping. They need to beg for 5 amps of power to turn the heater on.
Capcom, we want to get cryo O2 tank number 1 heater on.
The lights we got on now.
Yeah, he's got that suit compressor
Roger,
off.
copy
Right?
them, and we'd like to build up the pressure in O2 tank 1, so turn the heaters on manually. We'll watch the
You're going to
pressure.
keep track of that time, huh?
Roger that.
Okay, 26.9,
See a
huh?
5 amp
Yeah,
increase
26
there, EECOM?
Do you see a 5 amp increase there, Dick?
That's firm.
Okay, that's firm flight.
Okay.
26.7 volts, looks good. We'll watch the pressure.
Okay, this better works, or our fuel cell 3 will lose its oxygen supply. How does the pressure look, Cy?
ECS Econ.
Go.
It looks grim.
Yes, it does.
Got the 5 amps and no pressure increase.
Still,
AFT
it
flight.
just went down.
Position to evaluate.
It's going down. We're losing it.
Okay.
Yes, we are.
Look, we're in serious problem if we can't get any pressure down. We got to power down some more here.
That's right. And luckily we got the LEM.
Yeah, but that's not going to help this fuel cell.
That's right. We
We're
got to
like-
get it all the way down.
If we can't save that
Go ahead,
pressure,
Ian.
we're going to lose this third fuel cell.
stabilized considerably.
Raj.
Cy has realized it's an abandoned ship situation. He tells Flight to get the crew in the LEM and admonishes his peer for the LEM, called the TELMU, to better get ready for an emergency power-up procedure.
Okay.
Flight Econ.
Go ahead, EECOM.
The pressure in O2 tank 1 is all the way down to 297. You better think about getting in the LEM or using the LEM systems.
Okay,
Go
we
ahead,
got
Econ.
it.
Now let me tell you, we're in the danger of losing all 3 fuel cells. So you guys get yourself geared up, okay?
Roger.
Okay.
We're working all right.
That's your power procedure and all. You guys had one worked out already, I think, didn't you?
That's right.
Okay.
It's about 40 minutes after the accident. Cy has only one question for EPS now. How long do we have to bring the LEM up before running out of power in the command module?
EECOM. And
Go.
I think that's something we should have got started a while ago.
Looks like from the leak rate that we've got about 1 hour and 54 minutes left until we're down to
13,
100
this is Houston.
PSI.
We'd like you to give us a survey of your displays
About
on
the end of it.
MDC's
Flight, we're going to hit 100 PSI in an hour and 54 minutes. That's the end right there.
From there on, it's a mad rush for an emergency power-up of the LEM and a semi-graceful power-down of the CM. But there will not be quite enough time before fuel cell 2 conks out. Which brings us to the subject of the battery system. So we are back in DC land, where there are a few more buses we have not talked about yet, in particular Battery Bus A and Battery Bus B. On Apollo 13, which was lacking the big service module battery backup added later, These were powered by 3 small silver batteries at a measly 40 amp-hour each. These were only meant for powering the command module during the short re-entry. There was a provision to throw the batteries on the main DC buses to cover for a usage spike. This was done by connecting or tying the buses together, once again using a series of motorized relays. A few minutes into the accident, the ground asks the astronauts to turn on the AC bus tie, which will tie battery bus A with main A. Since only battery A was on the battery bus A with backup battery C on standby, this action connected battery A to main A to help out the struggling fuel cell 2.
Standby flight. Go EPS.
Let's throw a battery on bus B and bus A.
Okay.
Until we sack it out.
Okay.
We're getting under volts.
Flight EECOM.
Go ahead, EECOM.
Okay. If we want to keep...
Okay, Houston, are you still reading 13?
Standby, he's changed configuration. You got battery A on main A.
Some good ideas
Got battery A on main A now.
We got the 2 teams.
But as the situation gets worse, Houston needs to save the re-entry batteries and tells the crew to take the tie off. The astronauts immediately know why, realizing full well the consequences of having used part of a re-entry battery for the better of 30 minutes.
Flight EECOM.
Go EECOM.
We've really got to get that battery off the line and power down some more.
Okay, Si. Now, how long
The BMAG
You want to
is part
leave
of
this
the,
battery online?
SCS system.
I want to try to get it off
on
as quick as I can, but I need to get
Apollo
power
command
down.
module, of course.
You want that battery off the line now? 42 amps?
Yeah, we can take it off now.
Okay. Flight EECOM.
Go EECOM.
Let's take battery A off the main.
We can support the
That's
main
firm.
now on the 1 fuel cell, even with the cryo 2 going down.
That's a firm flight.
Okay, what's your worry level on cryo 2?
You say again, flight?
Okay, you want
I want to save the battery flight.
Okay. Turn battery A off, Capcom.
13 Houston, turn battery A off.
That's fine. We work for
Battery A off, Roger.
However, an hour later, at the tail end of the CM to LEM transfer, Fuel Cell 2 is not going to make it, and they desperately need to keep the command module computer and the inertial platform going until they are able to transfer inertial platform attitude angles to the LEM. They are now caught between a rock and a hard place. Flight Director Glenn Looney decides, rightly, to prioritize the transfer of the inertial platform over saving the batteries. They had just started to recharge battery A. Glenn reverses that decision promptly.
Return trajectory.
When we get a little lower, we're going to have them pull battery off, and we're going to have them put it on main bus A. We're then going to try to hold up the IMU long enough to get a course line in the LEM, and then we'll see whether we're going to keep that course line up or not. But for right now, we're running the profiles, and we'll have to determine that.
And keeping the course aligned they will. This was a mission-saving decision. They will do a free return trajectory burn a few hours later, and will not even have to attempt a platform star alignment for the precision abort burn at PC+2 after going around the moon. After that, they'll finally turn the LEM inertial platform and the computer off to save LEM power. Now, they are still not out of the woods in terms of power. They need to recharge their re-entry battery A that had saved them earlier. They will do it thanks to a cable meant to recharge the LEM batteries from the CM and a hacked procedure to use it in reverse, involving hundreds of circuit breakers.
There was a normal process of going to when you go into the moon and coasting to the moon, that the command module supplied a little electrical power to the lunar module. What you could do through a precarious route is figure out some way to have that power transfer come backwards. Somehow we could arrange the circuitry such that the only thing that you would be powering inside the command module out of all the hundreds and thousands of switches and circuit breakers was just this little thing called a battery charger. And we sent the crew over at this checklist, and they couldn't believe that we had devised this little multi-page checklist with hundreds of circuit breakers and switches and all that on it to actually get to the battery charger. But it worked.
All right, you are now Apollo spacecraft power system experts and should be able to follow the raw Apollo 13 accident audio. which is the best 2.5-hour customer service support call you'll ever hear. I'll link it in the doodly-doo. But let's get back to opening our inverter, which was supposed to be the focus of the video. I know, we got sidetracked a bit. And this one you identified...
Yeah, it has written on the side here, BP14 use only, which BP14, boilerplate 14, was the North American house spacecraft. So this was the spacecraft that they had in their Downey plant that they did essentially all of their integration testing on. Block 2 is very similar. From the specification control drawings we got, it looks like they may have combined all of these studs into circular connectors for Block 2.
But you can see what's laying on the floor of the capsule. It has the angle, so laying upside down. The 3 inverters were wedged under the communications equipment and had to conform to the curved edge of the heat shield, laying upside down. And somebody apparently had that in his aircraft or something. And it was, they had put goop on it, and there was some stuff that was not original. We cleaned it up. So it sat on a cold plate over here, which has a leak in it. It has a patch on the other side. And there is this really heavy copperish material that's supposed to be in between the two, but somebody had added some of the goop on it, which shouldn't be, of course, in a spaceship. So we removed it as best as we could. So this one has seen some amateur use, but it's a cool thing to have in your aircraft. Yeah, we don't know what's in there. There was screw missing. There's some stuff that doesn't belong. So we're going to look. There's stuff in there.
Yeah.
Right away there was something cheesy with that unit. Screws were missing, nuts were hurt falling inside, and we spied some strange looking material. So we took the depth-tech endoscope and got greeted by strange stuff that did not look quite right. A mouse.
Almost looks like it, but it's not.
So it doesn't look pretty inside. I'm not sure if it's asbestosy, but why would you put that in there? From then on, our voice will be a bit muffled because we all put on N95 masks, and it turned out to be a good decision. The screws or whatever was welded at the bottom, just some of them went loose, so this has had a tough life. Well, that's the weirdest piece of Apollo equipment we ever opened up. It's filled with this crap. That would be an insulator. It's very, very light. Yeah, I think you're right. It's, how do you call it?
Vermiculite.
Yeah.
Oh no, someone filled the thing with vermiculite. This was a test unit, so it was not potted, and therefore you were not supposed to fly it. So probably the person that used it in his airplane thought it would be a brilliant idea to pot it with vermiculite, which is very light and insulating. In fact, being an incredibly good thermal insulator, it is just about the last thing you want to fill a power supply with. And to top it off, it's extremely toxic. Vermiculite is laced with the most deadly form of asbestos. Good thing we put our N95 masks on, but we might still have gotten some of it. Okay, so we're back at the inverter. The deadly asbestos contaminated inverter should be fairly clean, but we masked up just in case. And well, it should be fairly clean. I'm sure there's tons of particles coming out of it still. It's a little sketch. So you see, this is the 28 volt input, and it's yay far from the heatsink or the holder of that cap over here. This is very tight. There's another point you can see over here. That is super tight. I saw another one that, yeah, I bent that one up because it was so close. I bent it up. So it's a little sketch. You have 3 of the same thing here. These guys are actually not transistors, they are diodes. There are only two connections to it. This one is left floating, and this is true for a lot of them. So that's on purpose. We would have a lot of capacitors to check. Plenty. 100 micro. Lots of caps on the side. Oh, that's an SCR. That is the main inverter. Lots of transformers, of course. There's a huge one in the middle. Underneath here, I think that's a big transformer. Some more out here. A bit of a scary monster, that is. We cleaned it off the best we could, but this unit is just too contaminated for us to work on it. To make things worse, there were obvious signs of corrosion. We don't have the schematics, but we have a good block diagram and a short description of how it works. It's all solid state. They use thyristors or SCRs, a buck converter, and magnetic amplifiers. The final up voltage conversion is done by rotating magnetic fields in a specially wound transformer to create an efficient power unit, although very heavy due to all the magnetics. We went as far as testing a few capacitors. We can't really work on repairing this unit since it's too contaminated. One bad capacitor and that would be the end of it. Testing the caps in circuit, I guess, would be the only thing we can do.
Yeah.
I bent it up because this was like a fraction of a millimeter.
Man, block one.
So my idea was just check a few caps. 3.8 microfarad. That starts good. 3.8, okay. 12 microfarads, so that looks okay. 100 microfarads. 92 microfarads. Well, that's pretty good, I would say. 550 microfarad, what's up? Some with too much capacitance? Should we complain about it? 47. Well, they are all reasonably capacitive. 34, 36, and 35. So I mean, they looks reasonable to me. Okay, so the one that are spot checkable, check okay. Over here, some over there. It's full of caps, basically.
Yeah, it is.
2.5 microfarads on the dot.
Yeah, 60 MFB.
This big fellow reads 2.5 micro, but it's written 68 on it. So I got the end out of it, so we can test it out of circuit. 65 nanofarads. Oh, that's bad. And this one looks like it's a capacitor no more. Yeah, so the 1.8 microfarad is from the connection it's attached to, and this one is not a capacitor anymore. Okay, so we have one bad one, which probably tells us we just give up. Let's see, 650 nanofarad. So we have one example of one that died, which is one too many, right? And there's so many capacitors all over the place.
Yeah.
We pack it all back together. we sent it back. Oh dang! I would have wanted to give it a try, but it's not in working order.
I'd be really curious to see what a block 2 inverter looks like on the inside, considering they didn't change the part number. So there's, they changed the dash number, but not the part number.
So I'm being nice to the next owner of this and making sure I put some tape is cloth tape. It's period correct from teletype. It's just the wrong color. And places where there were stuff that could be come in contact with the top cover, and our dodgy one behind the 28 volt input. So if somebody tries to power it up, at least you won't have these short circuits. So it's all buttoned up, and Eric, who did the bottom part with the cold plate, is reassembling it. But that's it. Bye bye inverter. I don't think we'll power it up. So we sealed it up in plastic bags and will not touch it again, and had to take a few days off to wash every surface in the lab. At least it taught us a bit about the command module power system and the incredible adventure of Apollo 13. So don't use collectible Apollo inverters in your aircrafts unless you have a team of cracked ground controllers to get your back, and see you in the next episode.